In this video, we're going to go over nucleophilic aromatic substitution reactions. So let's start with this example. What's going to happen if we have a benzene ring with a nitro group attached to it and also a chlorine atom? And let's react it with sodium hydroxide. What do you think the major product will be in this reaction? Now we're going to have to heat the solution. The net result is that the chlorine atom is going to be replaced with the OH group. So we're replacing the leaving group with not an electrophile, but rather a nucleophile. So this is not an electrophilic aromatic substitution reaction, but instead it's a nucleophilic aromatic substitution reaction. We are replacing a leaving group with a nucleophile. And so that's why it's called a nucleophilic aromatic substitution reaction. Now these reactions, they're the opposite of electrophilic aromatic substitution reactions. These reactions work better if you have an electron withdrawn group in the ortho position or in the para position. And so this ring is activated by an NO2 group. Now it makes sense because the ring is reacting with a nucleophile, and so the ring has to be electrophilic to react with a nucleophile. And nitro groups, which are electron withdrawn groups, they make the ring more electrophilic, thus more reactive to a nucleophile. Now let's go over the mechanism for this process. If you want to, feel free to pause the video and try to propose a mechanism for this process. Now we're going to have to draw out the nitro group. So we have a nitrogen atom that is bonded to two oxygen atoms, and the nitrogen has a positive formal charge. So the first thing that's going to happen is the nucleophile, in this case hydroxide, is going to attack the carbon that bears the leaving group, in this case the chlorine atom. And when that happens, the pi bond is going to break and we can put two electrons on this carbon. And so we're going to get a carbon with a negative charge. So this resonance stabilized carbanion intermediate is known as the Meisenheimer complex. Now, the negative charge can move about in the ring. So notice that the negative charge is in the ortho position. So if you were to put a nitro group on the ortho position, it can stabilize the negative charge. And that's why nucleophilic aromatic substitution reactions work very well if the electron withdrawn group is on the ortho carbon or on the para-carbon, but not on the metacarbon. We can't put that negative charge on the metacarbon. That is meta with respect to the leaving group, the chlorine atom. So this is ortho with respect to the chlorine atom. So now let's take this lone pair, let's form a pi bond, and then we can push two electrons on a para-carbon. So what we now have is a structure that looks like this. So the negative charge is now on a carbon that is next to the NO2 group, so it's on the para-carbon. And as a result, the NO2 group can store that negative charge. So here it is right now. It's on the para-carbon. And we still have the chloride leaving group. So the nitro group can now take the negative charge and put it on an oxygen atom. And so the electron withdrawing group, if it's in the right place, if it's in the ortho or on a para-carbon with respect to the chloride leaving group, it can store electron density, and then it can release it later in order to kick out the Cl or the leaving group, which is what it's going to do in the next step. So this is what we now have. So right now this oxygen, it had two lone pairs and now it has three. So it's going to take one of those lone pairs, form a pi bond, causing these electrons to move over here, causing this double bond to move in this region, and kicking out the Cl. And so this will give us our final product. So now we have an OH group instead of the chlorine group. And so that is the mechanism for the nucleophilic aromatic substitution reaction. So the net result is that we replace a leaving group with a nucleophile. Now these reactions are known as addition-elimination reactions. Now why do you think it's called that? In the first step, we added a nucleophile. So the hydroxide was added to the ring. So that's an addition step. And in the second step, we eliminated or removed the chloride leaving group. And so this mechanism is also known as the addition-elimination mechanism. Here's a practice problem for you. So let's say we have a benzene ring with a bromine atom and 2 nitro groups. Now this is going to definitely be a nucleophilic aromatic substitution reaction. The 2 electron withdrawn groups are on the ortho and the para-carbon. If we put it on the metacarbon, it's not going to help us out much. Now let's react it with sodium methoxide and heat. So what is the major product in this reaction? The first thing we need to do is identify the nucleophile. And the nucleophile is the methoxide ion. So the net result is that we're going to replace the leaving group with the nucleophile. So we're going to get an ether functional group. And so this is called anisole. But we have a nitro group on carbons 2 and 4 with respect to the OCH3 group. And so therefore this is called 2,4 dinitro anisole. So this is carbon 1, 2, 3, and 4. So that's the product for that reaction. Let's try one more example. So this time, we're going to have a poor leaving group, fluorine, and let's react it with an amine, butylamine. What is the major product in this case? So even the fluoride ion can be displaced by a nucleophile. Now we're going to have to heat the mixture in order to get this reaction going. But it does work, and in the end, we're going to replace the fluorine atom, and we're going to have an amine. I'm going to put the hydrogen on this side. And here is the butyl group. And then let's not forget to add the other NO2 groups. And so this is the product for this reaction. Now, I want to compare 2 reactions. So in both cases, we're going to have a chloride leaving group. But in the second case, we have an electron withdrawn group on the para-carbon. And in both cases, we're going to react it with sodium hydroxide. Now, if an electron withdrawn group is present, we're going to get the addition-elimination reaction, which is what we've been dealing with. And so the net result is that we're going to replace the chloride group with the OH group. So we've already talked about that reaction. Now what about the reaction above? Without heat, this is not going to work. To make it work, you need to heat it to a very high temperature, like 350 degrees Celsius. And then you could get phenol. However, the mechanism is not the same. If we don't have a strong electron withdrawn group present, the mechanism is going to be an elimination addition mechanism rather than an addition elimination mechanism. So in this reaction, we get the Meisenheimer complex where we get a resonance stabilized carbanion intermediate. For this reaction, we're going to get something else called the Benzyne intermediate. Now, before we get into the benzyne intermediate, I want to talk about something else. So without an electron withdrawn group, not only do we get a different mechanism, but notice how high the temperature must be in order to replace the leaving group. Whereas, let's say if you have one NO2 group, the temperature that's needed could be around 150, 160 degrees Celsius. Now, this temperature could vary depending on the pH of the solution and the leaving group. If you have a better leaving group, then it's going to be easier to kick it out. Let's say if we have two NO2 groups rather than just one. So the temperature that's needed to kick out the chlorine atom and replace it with a hydroxyl group will be less than 160. It can be around 100 degrees Celsius. And if you have another NO2 group, then it's going to be even less. It could be around 35 or 40 degrees Celsius. And so the more electron withdrawing groups that you have, the easier it is to replace the leaving group with a hydroxyl group. So that's something I want to mention before we get into this mechanism. So now let's go into that mechanism. So here we have chlorobenzene. And in the first step of this reaction, we are going to remove a hydrogen. So hydroxide is going to act as a base when it's heated to 350 degrees Celsius, and it's going to take off the hydrogen. And so we're going to get a negative charge on this carbon atom. And then once we have it, we're going to form a triple bond, and we're going to kick out the chlorine atom. And so this representation is known as the benzyne intermediate. So basically, it looks like a benzene ring with one of the bonds appearing to be a triple bond. Some books tend to view it as more like a diradical instead of a triple bond. And this triple bond is unusual because triple bonds tend to be linear, but this one is not. So we have a highly reactive system here. Now, in the next step, the hydroxide ion is going to attack the carbon, put in a negative charge on one side of that triple bond. And so here we've added the OH group, and now the triple bond is gone, so it's back to a double bond, but we have a negative charge. And so at this point, we need to react it with water or something that can protonate this carbon. And that's going to put a hydrogen on it, and the end result is that we have phenol as our final answer. Now let's go back to chlorobenzene. So how do you know when you're going to get the addition-elimination reaction versus the elimination addition reaction? If you have a powerful electron withdrawing group, it's going to favor the addition-elimination reaction where you get the Meisenheimer complex. That is the resonance-stabilized carbanion intermediate. If there are no powerful electron withdrawing groups, then we're going to get the benzyne reaction or the elimination addition reaction. And in the last example, we had to heat this to 350. So anytime you don't have a powerful electron withdrawing group on the ortho or para carbon, then it's going to be the benzyne reaction if you're reacting the ring with a nucleophile. In this case, we're using hydroxide. Now, if we use a stronger base, we can also get the benzyne reaction at a lower temperature. So in this example, we're going to use sodium amide. The NH2 minus ion is a much stronger base than the hydroxide ion. And the solvent is going to be liquid ammonia, and so the temperature is going to be around negative 33 degrees Celsius. So it's very low. And the end result is that we're going to replace the Cl with a nucleophile, in this case NH2, giving us aniline. Now let's work on an example problem. So let's say if we have para para-bromotoluene. What's going to be the major product if we react it with sodium amide in liquid ammonia? That should be NH2 at a low temperature. What's going to be the major product in this example? So feel free to pause the video and try this problem. It turns out that you don't get just one product, but rather you get a mixture of two products. The NH2 group can go on the para-carbon with respect to the methyl group, or it can be on the metacarbon. So why do we get a mixture of two products in this example? Well, let's find out. Let's go through the mechanism of this reaction to explain why. So in the first step, the base, which is NH2-, is going to take off a hydrogen, and we're going to put a negative charge on that carbon. And then in the next step, we're going to eliminate the bromine atom. So that's why it's called elimination addition. First we eliminate, and then we're going to add the NH2 group. So once the bromine atom has been eliminated, we're going to get the benzyne intermediate. So now we have the triple bond. Now once we have this benzyne intermediate, the NH2- ion, it can act as a nucleophile. It can attack the para-carbon, or it can attack the metacarbon. And so that's why we can get a mixture of two products. So let's attack the para-carbon first. So we're going to put a negative charge here. And then we know the last step is to add a hydrogen. So this is going to react with the solvent, which is ammonia. And then we're going to put a hydrogen on that carbon. And so this will give us the para product. Now, let's say if we wanted to get the other product. Let's say we want to get the meta product. What we need to do instead is attack the metacarbon and put the negative charge on the para-carbon. And so here the NH2 group is going to be added. And then the last step is to add a hydrogen to the carbon with the negative charge. And so that's how we can get the meta product. So if you have a substituent already present, and it has to be an electron donating group, because if it's an electron withdrawing group, it will favor the addition elimination mechanism rather than the Benzyne mechanism, which is elimination addition. So because we have this electron donating group, it's going to favor the Benzyne reaction, where we can get a mixture of products. So this is our final product for the second product, the meta product. Now, let's go over one more example. So in this case, we're still going to have two substituents. That is the same substituents in the last example, but this time they're not para with respect to each other, rather they're meta with respect to each other. So we have meta-bromotoluene. And let's react it with sodium amide and liquid ammonia. So what products can we get in this reaction? Feel free to pause the video and try it. It turns out that we can get a mixture of products, but not just two products, but rather we can get three products. So we can replace the bromine atom with the NH2 group, or we can put the NH2 group one carbon away from the bromine atom on either side, because we could form the triple bond here or here. And so we can get a mixture of products. So here is the ortho product, and the last product that we can get is the para product. Now let's talk about why we can get those three products. So first, let's draw the original reactant. So here is the methyl group, and here is the bromine atom. Now the base can remove any one of these two hydrogen atoms. So let's call this hydrogen A and hydrogen B. So initially, let's use the base to remove hydrogen A. If it goes to remove hydrogen A and expelling the bromine atom at the same time, we can get this benzyne intermediate. So we'll have a triple bond between the bromine atom and hydrogen A, or between the orthocarbon and the metacarbon. So now when NH2 minus comes in to attack the benzyne intermediate, it can attack at the ortho position or at the meta position, giving us these two products. Now, if we remove hydrogen B and the bromine atom, we can draw the triple bond here. Now, we may need to rotate these three double bonds, so we may need to draw the resonance form of that benzene ring. So once we have this form, the base can attack at the metacarbon or it could attack at the para-carbon. And so that's why we get three different products in this example, because the base can remove any one of these adjacent hydrogen atoms. And so we can get the triple bond in this region or in this region.